I began by reminding you that we were supposed to talk about the direction of descent of a differentiable function over the whole R n. We are trying to minimize a differentiable function over whole R n, and we are going to talk about the direction of descent. But means if I move along that direction, my functional value would decrease because I am minimizing. The important part here is this, that I have also given you homework to take this optimization problem, a linear programming problem in 2 variables, but 3 constraints, and I told you to draw the feasible set of this problem. I hope you have tried it out, but after we do the direction of descent, we will try to solve this problem. So, if I have a local minima, what would I have? So, if I have a local minima at a point x bar, say in R2, all the drawings are in R2 as you know, then I can find a ball of radius say delta radius delta such that, so if you have x bar as a local mean, then you have f of x bigger than f of x bar for all x element of b delta x bar, and you know what the ball means. So, any x in this disk would satisfy this. Now, what it means that this is my vector x bar, and if I take, I want to remove this stuff. So, here we see the drawing where x bar is the point and there we have drawn a disk around it. So, take any direction w, w is actually I would say slightly larger possibly, this is the direction w, and this vector up to here is lambda times w, and this when we add them x bar plus lambda w, I get a vector here, a point here which is inside the ball. So, there exists lambda greater than 0 for any w, for any given w, such that f of x bar plus lambda w is bigger than f of x bar. By Taylor's expansion, I would again leave you as a homework, show that f of grad f of x bar times w is greater than equal to 0 for all w in R n. This is exactly what you have as an optimality condition, in fact, when we are talking about a local minima of a differentiable function. In fact, here of course, any w you will get grad f x bar equal to 0 because you will put w equal to minus grad f x bar and so and so. But this is the basic optimality condition. What does it mean? If x bar is a local minima, then this is happening. Now, if there exists a w, or to say d, maybe it is better to write d because talking about direction. If there exists a d in R n such that grad f of x bar d is strictly less than 0, then x bar is not a local mean. Of course, because if p implies q, local mean implies this, then not p, which is this, not implies not q implies not p. So, this is just a logical rewriting of this thing. So, if I have a d like this, what does it give me? So, it gives me the following. You can show by just the using again Taylor's theorem that there exists a lambda naught greater than 0 such that for all lambda between 0 and lambda naught, f of x bar plus lambda d is strictly less than f of x bar. So, how do I check as a homework? Check it out as homework. Now, if I have done this, so which means what? That I have gone to a point in Rn which is x bar plus lambda d. I have moved along the direction d from x bar, and I have got a point, there is a lambda for which I will get a point such that the functional value is strictly less than the functional value here. So, even if I do not have a local minima at x bar, I am trying to move in a direction so that my function value decreases. So, any d which satisfies grad f x bar d is strictly less than 0 is called a direction of descent. So, this d is called a direction of descent. So, we will be now talking about the direction of steepest descent. By our standard notions of a dot product, this is nothing but the norm of f x bar, oh it was d, into norm of h, sorry norm of d, the cosine of theta, where cos theta, where theta is the angle between grad f x bar and d. This is the following fact. Now, what is the minimum value? Where, how can I minimize this value? Suppose I get a d even if it is strictly less than 0, it does not matter. What is my minimum value? My minimum value of this would be attained. So, the minimum value of this function is attained when cos theta is the most negative. So, grad f x bar d is minimized when cosine of theta is minus 1. So, when cosine of theta is minus 1, what I will get is theta is equal to pi, cos theta minus 1. Is theta equal to pi or some multiple of pi? So, pi, 2 pi, 3 pi, 4 pi, whatever. Cos n theta is same, it is pi, is minus 1, because cos theta will come down to pi and go up, pi will again come down to minus 1 at 2 pi. So, cos n theta is minus 1 to the power n, right, sorry, is minus 1. So, in this case the two vectors cos theta is minus 1, the angle between them is cos 0 is 1, cos pi is minus 1, cos 2 pi. So, 2 pi is not is again 1, and cos 3 pi is again same as cos pi is minus 1. So, cos n theta is minus 1 to the power n. So, which means the angle between them is anyway theta is pi or any odd multiple of pi. So, if theta is pi or n pi when n is odd, but because we are talking about vectors, their angles are, and if you take a vector with this angle, does not matter. So, which means that our case we require theta equal to pi, our case, because we are talking about vectors, say in 2 dimension. So, theta is pi, right. Now, what would be then h? So, norm of grad f x bar, norm of d. So, this into minus 1 minus is equal to grad f x bar d. So, what should be d? You see, because theta is equal to pi, so they have two vectors grad f x bar and d. Angle is theta, but this angle is pi, grad f x bar and minus d are in opposite direction. So, d is the negative of grad f x bar, that is what is the required d for which this functional value would be minimized, and this would be the value. So, means now grad f x bar with a minus sign would only give me norm of grad f x bar if grad f x bar is non-zero, which is why we are doing all this. This is strictly less than 0. So, it is a direction minus grad f x bar is a direction of descent, and because it minimizes this value, this particular value of d equal to minus grad f x bar is called the direction of steepest descent. So, once you know that which is the direction of steepest descent, you will ask the question, in our setting what is the direction of steepest descent. So, if I have minimize C transpose x, Ax equal to b and x greater than equal to 0. So, if I just take this function C transpose x and I find the gradient of f x, which is c. So, direction of steepest descent of this function is minus grad f x equal to minus c. So, whichever direction is c, I will just have to move in along the opposite direction to get a decrease in the function value. So, now we will try to solve the problem in a geometrical fashion that we had given yesterday. So, I will rewrite the problem because you might have forgotten about it, because a few slides back. So, minimize minus 2 x 1 minus x 2, which is my z value, objective value. Is usually as a standard to write in. This is how things are written in linear programming. I will give you references, but just listen to me for the time being. So, in this case my f x is minus 2 x 1 minus x 2. So, grad of f x is minus 2 minus 1. So, direction of steepest descent Now, let me draw the feasible set of this problem. So, my thing is minus 2 x 1 minus 2 x 2. So, this is my x 1, this is my x 2. So, it is 0, 1, 2, 3, 4, 5, 6, 7, 8 and so forth, 1, 2, 3, and do not bother about this part because this and so on. So, something x is less than or equal to 4. So, all my x must pass through this point. No x can be chosen bigger than 4. Okay. Then this is the first thing, then we look at x 1 plus x 2 less than or equal to 5. So, it is passing through this. this line, anything inside this. Okay. Now, 2x1 plus 3x2 is less than 12. So, if I put here equal to, then if I put say x2 equal to 0, then x1 is 6, it is this one, and if I put x1 is 0, then I get 4. So, it is connecting this 4 and 6. Okay. Right. Now, what is my feasible set? My feasible set is this one. So, now I will rub the parts which are not in the feasible set. So, you will see the complete feasible set. And x1, x2 greater than or equal to 0 we have chosen. So, this is our feasible set. So, there is not a straight line here, there is a slight curve here. So, what is my direction of descent? What is my problem here? Minus 2 x1 minus x2. So, when x2 is 0, so here you see, if I look at this curve, so this is constant. So, I can put here something, say this is equal to say 2, 3, whatever, say something, it will be a curve like this, and 2, 1 is my direction of descent. So, it is 2 and 1, 2 and 1. So, not writing, so this is my direction of descent. So, if I move this whole thing along, it is not exactly correct here, is slightly, because that C of C transpose X has to be perpendicular. So, it is something like this. This is my objective, 2 minus 2 x1 minus x2 is some constant C. So, now I am moving it along this direction. So, I come and touch here, come in when I put my C here. So, I am coming, then I am inside the feasible zone, but I have to move along the direction of steepest descent. As I move like this, my functional value is decreasing. Here you see I am still in the feasible set, but then there comes a point where I simply go out of the feasible set. So, I have a point where here there is a bend. So, I am coming and touching at this point, and if I move a little bit off, I am outside the feasible set. So, remaining in the feasible set, this is the maximum drop in the value obtained. So, this point which I am unable to. So, I am coming, this is my feasible set, and I am coming like this, I am coming like this. You see, finally I come and touch here, this point, this bent you see here, this particular bent, this bent, this corner point. So, what happens is that as I am moving along this direction, I am bringing it, and once I am inside the feasible set, I am fine, but those are the values I am required to bother about, the functional value of the objective for these points. But as I move push the line parallelly, you see the functional value of the objective, this z keeps on decreasing, because that is the direction of descent, and it comes and comes and comes here, 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 and then it is in a position when it passes through this point, because I am moving it continuously, it occupies all the space here, not discretely, it moves continuously. It comes to a point here when it is in this form, and at this point if I just move a little bit, I am outside the feasible set, and that is it. So, then once it is in this situation, this is the only contact it has with the feasible point. There is a feasible value, a feasible point which is touching it, and because if you move in this direction you get the maximum descent. So, the maximum drop in the value comes when it comes here. So, this point is my optimal point. So, which you can figure out what it is, which I will not do, figure it out. It is for you to figure out optimal point. Just you take intersection of x less than 4 with this one. So, the interesting part is that this is how we are looking into the using this direction of descent to find geometrically the minimum point. This is the optimal point, and there is a little observation which you might say is too early to decide, but this observation is an important observation. The minimizer this can be proved and will be proved later. Now, let me go into certain aspects of the simplex method, which is very, very important. First thing to know that if you look into any book on the simplex method or any book on linear programming where simplex method is discussed, there are books on linear programming where simplex method is not discussed. Okay. So, one might say, oh, what a strange thing to say, but there are books on interior point methods where it is not discussed. For example, the book by Stephen J. Wright, which was published by Siam, called Primal Dual Interior Point Methods for Linear Programming. So, if I take this my standard LP problem, a standing assumption is that the rank of A is M. Now, the question is this assumption a good one? We will end our discussion today by proving this fact that yes, it is indeed a good step, by showing that this assumption is fine. Now, look at the constraint system A x equal to b. I can write this constraint system as follows. So, this can be equivalently written as A x less than equal to b and minus A x less than equal to minus b. This is same as A x greater than equal to b. So, these two combines to give you that. Now, in both the cases I can apply the law of adding a slack variable. So, I can write this as A x plus s is b, A is a m vector, and minus A x plus t is minus b, where s and t are greater than equal to 0. So, once you do that, then the system A x equal to b can be equivalently written as I add the x greater than equal to 0. So, this is the system. So, I here is the identity matrix, I is the m cross m identity matrix. So, I is nothing but diagonal 1 1 m times now. If I take this matrix and I write this as A tilde, it is part of your homework to check up that rank of A is twice of m. Check as homework. So, give me any system of A, I can always convert it into a system where using slack variables into a system where I have a matrix which has full rank. There are m rows, 2 m rows. So, rank is 2 m. So, it is full row rank. So, A tilde has full row rank. So, give me a system like this, I do not bother about the rank of A, I can convert it into a system where I have a matrix which equivalently expresses the constraint system, but has full rank. So, without loss of generality, which that is usually written as like this, without loss of generality, we can assume that rank of A is m. Once I know this thing, it is very important to know about certain aspects of convex sets called extreme points, because these are the things that will come up very soon, because the solutions of the linear programming problem would lie in some of these corner points or extreme points. You see these points, this point, this point, this point, this point, this point, these are corner points of this nice looking convex set or a polyhedral convex set. This is actually a bounded polyhedral convex set which is called a polytope. So, I just remind you once again by the name bounded polyhedral sets. Now, once I know this, these points are called extreme points, and why they are called extreme points will soon come up with a definition. It is something you and I understand that these are corner points, like if you have a convex set like this, you and I understand these are the extreme points, very bad corner edges. This is my whole set. But how do I mathematically talk about this point? What is the feature of this point? The feature is that I cannot take two distinct points on this set and express this point as a linear combination or a convex combination of these 2 points. Suppose I take this point and this point, 2 distinct points on the given set, and I join them, I will get some point here. It will never become a point on the corner. A point on the corner can never be expressed as a convex combination of 2 distinct points of the set. These are the characteristics of extreme points. So, I can define an extreme point as a follow. Let S be a convex set then a point x is called an extreme point, that is you cannot express it as a convex combination of 2 points when lambda is strictly between 0 and 1, but that is excluding these 2 points. If you take all such points, for example, on this line, this is not an extreme point, this is not this point. So, you cannot find any 2 distinct points on this set so that if you join those two distinct points by a line segment, this extreme point would be one among those points, a point on the line segment other than those 2 points. So, this is a point x obviously in S. If you are not happy, then I can write like this, that point x element of S is called an extreme point of S if for x1 and x2 element of S and lambda element of 0 1 x equal to lambda x1 plus 1 minus lambda x2 implies that x1 is equal to x2 equal to x. The only possible convex combination is when x1 x2 is equal to x. It cannot be any, there cannot be two distinct points whose line segment other than them the 2 points itself an extreme point lies. No such extreme point will have the property of being a proper convex combination, not the extreme those points themselves, the proper convex combination of the two distinct points. For example, here I have finite number of extreme points, such sets are called polyhedral polytopes, actually finite bounded polyhedral sets. But there are some sets which have a infinite number of extreme points. Consider a circular disk which is a convex set. So, you take a circular disk, the boundary, this line and curve and then everything inside. Now, any point on this curve cannot be expressed as a linear combination, proper linear combination of two distinct points x1 and x2 on this set with lambda belonging to 0 and 1, that is lambda is neither 0 or 1. So, I am excluding those two extreme points, it is in the interior of the line segment joining the 2 points, it is not possible. So, this is an example of infinite extreme points. Of course, it goes without saying that the extreme points are actually in the boundary. If it is not in the boundary, then I can do this. If it is not in the boundary, then I can always get 2 points where such that this expression is true. So, it has to be in the boundary, right, because this is not true. Now, I will try to give you an homework, figure out how to show that extreme points are in the boundary. So, take a closed convex set, So, if there is a famous theorem called the Green-Millman theorem which says every compact convex set is the convex hull of its extreme point. So, if K is convex and compact, and K is the convex hull of its extreme points, which I say mark as extreme points of K. This is the famous Green-Millman theorem. So, what we essentially want to show that if you give me a minimizer, I will show of a linear programming problem, I will show that that minimizer corresponds to an extreme point on the feasible set. And this is the idea that we are going to explore in the next class and which will lead us to the simplex method. So, we will not do all the proofs in detail, but some of the proofs would be done to show you some ideas, but not all the proofs, because we cannot spend a huge number of time on linear programming problems, but just to give you a basic idea of of this very particular class of convex optimization problems. Okay. Thank you very much.